In this video, we continue to take a look at Markov chains. Markov chains are sequences of state matrices related by this equation, x to the k plus 1 subscript, as we denote it, equals the transition matrix P multiplied by x to the k. So x with the k sub 1 subscript is the k plus 1th state, and we get that by taking the transition matrix, also known as the stochastic or Markov matrix, and multiplying that by the previous state. So to find the state matrices, recall that we are repeatedly multiplying the initial state matrix x sub 0 by the matrix of transition probabilities P. So the first state matrix x1 is P times x naught. The second state matrix x2 is P times x1, which is just P times x naught, or P squared times x naught, and so on. So in general, we've said the nth state matrix of a Markov chain is P to the n power times x naught, which we summarized as x to the n subscript equals P to the n power times x naught, where x naught is the initial state matrix. So now we're going to add the definition of a regular stochastic or Markov matrix. So a stochastic or Markov matrix is regular when some power of P has only positive entries. So we want to take a look at these for examples and see which of the following stochastic matrices are regular. So first, just to verify that they're stochastic, we can check to make sure, do all the columns sum to 1? So if we check that in matrix A, that is true, all the columns sum to 1, so that makes the criteria for being a stochastic matrix. There's also all values are between 0 and 1, they're probabilities, that's our other criteria. So matrix A here, there's no work for us to do because we see that all the entries are positive, so we are in good shape. So A, we can say, is regular. All right, matrix B has a 0 entry. It is stochastic because all the columns sum to 1, but we need to check to see if we can get a power where there are only positive entries, no 0 entries. So I'm going to go enter matrix B over here in Simpy. We'll say B equals matrix, and then our values in B in the top row are 1 and 0.6. And in the second row, our values are 0 and 0.4. So let's check out what B squared is, or B multiplied by itself. We do B and then we do the double asterisk in Simpy to get the exponent, and we do 2 there. And oh, we're still getting a 0 there. All right, let's check B to the third power, see if that gives us a positive power. We're still getting a 0 in that 2, 1 position. All right, let's try B to the 4th power. And we're still getting a 0. So if you think about how this matrix multiplication is working, when you're multiplying these successive powers of B, think about that with the 1 and the 0 in the first column, when you multiply, well, let's just go write it out instead of me trying to describe it. So if you're multiplying 1, 0, and 0.6 and 0.4, as our columns, when you multiply here, you're always multiplying these values. So the 0 down here in row 2, column 1 is always going to give you a 0 added when you do the first entry, but then when you come and multiply the second row times the first column, you're going to get a 0 times, so down here you're going to have 0 times 1 plus 0.4 times 0, and you're going to end up with a 0 again. So there's no way to get rid of the 0 here, so we'll say that this is not going to be regular, because you can imagine if you keep multiplying with that 0 in that same position, all of your 2 by 2 matrix multiplication is going to result in a 0 down there. All right, let's go check matrix C. And our first row of matrix C is 0, 0.4, and 1. And you can verify all the columns add up to 1. So this is a stochastic or Markov matrix. The second row is 1, 0.20. And then the last row, since everything in the center column sums to 1, is 0, 0.4 in the center column, and a 0. All right, so we verify matrix C is typed correctly, and then we can check out, well, what is C squared? Oh, okay, well, we got rid of some of those zeros. Let's check out what is C to the third power. Hey, all the zeros are gone. So the third power of matrix C gives us all positive non-zero entries. So we can say that matrix C is regular. And then we'll go check matrix B the same way. Of course, you could multiply these matrices by hand, but we see it's much easier to let technology do that for us. I'm just entering the top row of matrix B. The second row of matrix B is 0.5, 0, 1. The 1 or 0.1? It's 0.1. And the third row is 0.2, 0, 0.4. And we can hit D and enter and verify we typed our matrix correct. So let's look at if we multiply D by itself to the second power, and we're in business. We have all positive entries, non-zeros. So we can say matrix D is also regular. All right, now we are told this relationship. We're going to prove this later on when we learn more about eigenvalues, that when P is a regular stochastic matrix, the corresponding regular Markov chain, P times X naught, P squared times X naught, P3 times X naught, and so on, approaches a unique steady state matrix. So in this example, we're going to determine whether this matrix P given to us here is a regular matrix. And then we are going to find the, let's just say, the steady state matrix of the Markov chain with P as the matrix of transition probabilities. I'll edit my text real quick. Oh. Now it says steady state, what I wanted to say. All right, so we need to first verify that P is regular. So I'm going to go input it into SIMPy and start checking the powers of P. The first row of P is 1/4, and we can enter the fractions just like this in SIMPy. And the second row also starts with 1/4, and you can verify all the columns of P add up to 1. So this makes us a stochastic or probability matrix or Markov matrix. Markov was a Russian mathematician. You can go read about him on Wikipedia. There's a nice page with information about him, and he is who Markov chains are named after. Okay, I've entered my matrix here. I'll type P and enter to verify I entered it correctly with no typos. And now let's check the second power. So P to the second power. All right, all the entries are positive and non-zero, so we are in business. Remember, if you want this in decimal form, you can type dot eval f function with the parentheses afterwards. Oh, I didn't like that. So just kidding. I think you might have to name it. It didn't like my syntax there. Okay, so let's try some different syntax. Let's name this object before we try to evaluate it as a decimal. So we'll do p2 equals p to the second power. And then if we type p2 dot eval f function with the parentheses there, voila, we get our decimals. So Simpy just wants us to name the matrix of the exponent before we evaluate it as decimals. All right, so we can say these are all positive. They're all between 0 and 1. So P is a regular matrix. So that's the first part of our problem. So my note here is to say that this is a regular matrix since P to the second power has all positive entries. And now we want to find the steady state. So we are looking for the steady state matrix X bar as we indicated with the bar on top. And so we want to find where when we multiply the transition matrix by the steady state matrix, we get out again the steady state matrix. So we can write this as our matrix, treat our transition matrix here as a coefficient matrix. So I'm just copying our transition matrix here as a coefficient matrix. And we can think about, well, let's multiply that by some steady state matrix. It's going to correspond with these values in a column vector, so values x1 through x4, and we should still get out x1 through x4, because if this is a steady state matrix, when we multiply the matrix of transition probabilities P by the steady state matrix, we are still expecting to get out the steady state matrix. So let's translate this into a system of equations. So we are going to have 1/4 x1 plus 1/3 x2 plus 1/2 x3 plus x4 equals x1. And that is based on this first coefficient matrix times the column matrix x1 through x4, and that shall be equal to x1 through x4. Our second equation in our linear system will be 1/4 x1 plus 1/3 x2 plus 1/2 x3 all equals x2. Our third system equation here is 1/4 times x1 plus 1/3 times x2. All is going to equal x3. So you can see, going back, these are just the coefficients corresponding with transition matrix P. And then our last row here is at 1/4 x1 going to equal x4. All right, so we can make use of the fact that x1 through x4 have to add up to 1. And so we know, okay, if we subtract back, we can move these values back over. So we know 1/4 x1 minus the x1 is going to simplify to be negative 3/4 x1. And then all the rest of our equation stays the same, plus 1/3 x2 plus 1/2 x3 plus x4 equals 0. So I just took this x1 and subtracted it from the 1/4 x1 here. Then in the next row, I'm going to take the x2 and move it over and subtract it from the 1/3 x2. And so this gives us 1/4 x1 minus now 2/3 x2 plus 1/2 x3, because the rest of the linear equation remains unchanged, equals 0. And then we get in the next row, I'll switch colors. So taking the x3 and subtracting it from right here where there's no value. So we're going to have 1/4 x1 plus 1/3 x2 minus x3 equals 0. And then we've got one more row here. So we'll subtract that x4 from the other side. So we'll have 1/4 x1 minus x4 equals 0. And then we know, because this is a stochastic matrix, that all of x1 plus x2 plus x3 plus x4 add up to 1. So I'm adding that as one more row in this system. And so now we'll head into Civvy and find the solution. So we'll say M equals matrix. All right, so my first row is negative 3/4, 1/3, 1/2, 1, and 0. Based on the system of equations we wrote. My second row is 1/4, negative 2/3, 1/2, 0 for the x4 column and 0 for the solution column. My third row is going to be 1/4, 1/3, negative 1, and then 0 in the x4 column and 0 for the solution. So remember, my values are just based on this system that we wrote right here. So I'm just pulling the coefficients and augmenting the matrix with the solutions to type these values in. So I'm on the fourth row, which corresponds with our fourth equation here. So it's going to be 1/4. So that was the coefficient on the next one. Then I have a couple of zeros, a negative 1, those are minus x4, and a 0. And then my last row is going to be all 1s, because we know x1 plus x2 plus x3 plus x4 have to total 1 here. All right, let's check my matrix M to make sure the coefficients match my equations. And then we want to solve this, so we'll do reduced row echelon form. So we do m dot REF parentheses, that brings the reduced row echelon form function. And then I only want the first return, I don't need to know the column pivots. So in brackets, I put a 0. And here's our solution. So this tells us x1 is 2/5 or 0.4, x2 is 3/10 or 0.3, and x3 is 1/10 or 1/5 or 0.2, and x4 is 1/10. So we can write our matrix, our steady state matrix, x bar as, you could say 2/5, 3/10, 1/5, and 1/10. Or you could, in decimal form, say 0.4, 0.3, 0.2, and 0.1 as our solutions. So that is the process for finding the steady state matrix for a permutation matrix or a stochastic or Markov matrix P.